Hello everybody. Today we will learn about the alternating current, or known as the AC current, because it's alternating and its value goes up and down, negative and positive and all these things. So that's why it's called an alternating current, opposed to the direct current, or DC. So DC current comes from like stable, not stable, I would say steady resources, just like those from the battery, for example. So these are called DC. So there's the AC current, alternating current, and DC current, direct currents. Okay. So first of all, there's like this power source generator. It uses, for example, a dam water coming down, and there's turbines that are rotating, and those turbines have a lot of coils in them, rotating about a magnetic field, or created by a magnet, a huge magnet, and the way they are rotating, they reverse current as they are making it. Okay, so the current that gets out of this looks like something like this. It goes up and down, up and down. All right. Now, of course, we can use that, and this is useful. The only time it's not useful when it is zero here. Okay, but it's useful here, useful here, useful in between, and so forth. Okay, so this is called the AC current, and if we want to describe in a circuit what the AC resource look like, it looks like this, just to give it a symbol. So this would be something like R. This would be something the voltage or AC signal source, and so forth. Okay. So the current that is coming out from this looks something like that. Goes up and down, up and down, and it repeats this on a very everlasting cycle. Okay, so as you can see, from here to here, that's a cycle, or from here to here, that's a cycle, whatever you want to call it. The distance between here and here is known as lambda, which is the wavelength. Now, this is probably given with a frequency on time, right? So this is time. So let's say the cycle repeats itself every time, whatever that period is. So this time is a specific time. We call it the period. Okay? So we have to call it this way. And if that was, for example, the signal itself, whatever that signal is, so I'm going to make it the current. Okay, so this is the current, and it's alternating with respect to time. Okay, this is a sine wave. As you can see, the sine starts from 0, goes up to a maximum when the angle is 90 degrees, or pi over 2, goes down to 0 again at pi, goes to negative 2 pi over 3, and so forth. Here is a 2 pi, which is the same as 0, and it keeps going and going and going. All right. So this is the period, and it consumes certain amount of time. So the amount of cycles you can have in 1 second, we're gonna call it the frequency. So the frequency is number of cycles per second. Okay, since it's number of cycles per second, so the unit of the frequency should be equal to second minus 1 over, or 1 over second. Okay, so since this is a sine wave, so we can call it sine theta. And according to what we learned in the past, theta is actually a distance. It's an angular distance or angular position. And any position is given by the velocity times time. Now, this is angular velocity, because this is angular position. Okay? So I'm going to call this I. I is equal to sine omega times t. And of course, it's not only the sine, because this is I. This will be the maximum value of it. So I is equal to I naught sine omega t. Now this omega is, as we learned it, is equal to, it's called the angular frequency. And the angular frequency is equal to, since it's angular, you multiply it by, you bring the frequency and multiply it by 2 pi. So I can write this equation again as I is equal to I naught sine 2 pi times the frequency times t. Okay. Now the same thing exactly applies to the current, the voltage signal. Since the current goes up and down, the voltage imitates the motion of the current. So if I want to say the voltage, so this would be V and this would be T, the voltage would exactly imitate the same motion or the same kind of like format or form as the current. So this would be lambda, or the wavelength, or you can say this is lambda if you want to, and of course this is also the period, and you have a maximum voltage. You're going to call this V naught, and then you can say V equals V naught times sine 2 pi f t. Okay, the same as the current. I forgot to mention that this part here where the current is maximum, you can call it I naught, where I naught means maximum current. All right, so now let's actually look into more of this. Now we know that the power, for example, the power is equal to I times the voltage. All right, now let's see how that's affected. We can actually write this here. We bring I is equal to I naught sine theta. So I'm going to say I is equal to I naught sine theta 2 pi ft. So I'm going to leave that for a little bit. Then V is equal to V naught. So I'm going to multiply this V naught and sine 2 pi ft. So sine times sine, that would be sine square 2 pi ft. Now this is a good equation. However, in real world applications, this is not a useful one. So we need to look for a more useful and meaningful kind of like power. Why? Because this is alternating all the time, and as you can see now, it's always positive. If I want to plot this one, it's going to look something like this. As you can see, it's always positive because sine squared does not have any negative value. Anyway, so this is kind of like not the best one we can use to represent the average or the power that we need, because we need to look for a more useful concept. And the more useful concept is known as the average power. And the average power, we're going to call it P average. So P average will be exactly somewhere like in the middle of this, right? Because it goes between the maximum and minimum. All right, so this is 0, this is the maximum, so it should be 1/2 of what we're looking for, which is V naught times I naught. So it's 1/2 maximum value of the current and the voltage. All right, so we can write this down as V naught under the square root of 2 times I naught under the square root of 2. Okay, now we can actually look more into this, because this quantity here, they gave it a name. They called it the root mean squared value. So that's the root mean squared. So this is the voltage root mean squared, and this is the current root mean square. So instead of like root mean square, they write it like this. So they give it I root mean square is equal to the maximum value of the current divided by root square of 2, and the V RMS is equal to V value maximum divided by root square of 2. Okay, so basically this power here, average, comes as I RMS multiplied by V RMS. Okay, and this is a very more useful quantity. All right, okay, let's look at this example together. We have an amplifier. An amplifier is an electric instrument that is used to boost the signal. Like if you have an amplifier, for example, in your car radio or car CD player, because it can boost the volume of the sound, and it gives you like a large sound. So that's what an amplifier is. This amplifier receives a solenoid voltage. Solenoid is another instrument in the electric world, and it looks like a swirly, kind of like a wire, and they have certain applications in circuits. So an amplifier receives a solenoid voltage signal with a peak-to-peak value of 24 volts. Okay, peak-to-peak value, what is that? Let's see. So if I draw, this is, if you think of it as like a signal, peak-to-peak, so that's peak and that's peak. And they say peak-to-peak is 24 volt, which means that this here is 12 volts, okay? And you can say this is V naught, this is V, and this is T. All right. If the resistance of the amplifier is 18 ohm, okay, we have the resistance of the amplifier is 18 ohm. Let's see what we need to find. Find RMS voltage. Okay, RMS voltage. We know that V RMS is equal to V naught over root square of 2. And that would be equal to 12 over root square of 2 volts. I'm not going to calculate it for now, okay? Now, also, what do we need to find? RMS current. First of all, we need to find the maximum current, okay? We know that V is equal to IR, which means that I is equal to V over R. If V is equal to 12, maybe that would this can be like I naught now and V naught. This would be I naught and V naught and I naught. That's fine. It depends on what you're trying to use. So you can change that RMS, average, doesn't matter. Okay, because it's the same thing if you change it all the way in the equation. So I naught is equal to V naught over R. What is V naught here? V naught is 12 divided by R, which is 18. And 12 over 18 is 2 over 3 current, that's amps. So that's what? That's the maximum current. If you want to find the RMS current, RMS should be equal to I naught divided by root square of 2. So this should be 2, right? Over 3 divided by root square of 2. And that's the answer for the RMS current. Now you need to find the average power. The average power is equal to V RMS times I RMS, and V RMS is equal to 12 over root square of 2 and times the current RMS, which is 2 over 3 divided by root square of 2. Now root square of 2 times root square of 2 is 2, okay? 12 divided by 2, that's 6. 6 times 2 is 12 over 3, and this whole thing will be 4 watts. Okay? Now what else do we need to find? We need to find the maximum current. We already did here. And finally, minimum current. Okay, if the maximum current is 2 over 3 amps, minimum current would be minus 2 over 3 amps, because it would be at the bottom here if that was the current. Okay? And that's it for now. Thank you very much.